Audio data and analysis are transforming how computers interact with people and provide useful services. Digital assistants use natural language processing that is driven by machine learning to translate audio signals into text. Audio data is used to detect intrusion, anticipate rotating equipment failure, such as in pumps and turbines, and acoustic location of firearm discharge in cities. This tutorial is a demonstration of audio data analysis with an application to detect a nearby drone. The first step is to import libraries for audio analysis. To get access to this module, go to APMonitor.com/DDE. And once you are there, you're going to reach this access under audio. And so select that, and then you'll see the Python audio and Google Colab link. You can select either one. I'm going to do GitHub link right here. You can, if you just right click it, you can select save link as, and then you can save your IPython notebook to your desktop. The other way you can do this is just open it up through Google Colab and then run it through a web browser. So let's go through this together. I'm going to import audio libraries we need for analyzing. We're going to first of all pip install pydub. If you don't have it already, you need to install this. This will convert the stereo signals into a mono signal. Okay, it says I already have it. If you don't have it and you installed it, then just come here to kernel and then restart your kernel, and then you can comment this out. Okay, and then we're going to import Numpy. We'll import Matplotlib, and also from Scipy.io, we'll import wavefile. And then we'll also import signal from Scipy, and then from pydub, we'll import audio segment. So let's import these packages first. And then we're going to download an audio file that's just used as an example here. All right, so here is URL lib request. We're going to get drone1.wavefile, and here's our URL where this can be found, and we'll go ahead and retrieve that to our desktop or wherever we're running. All right, so here it is right here, the wave file. I'll go ahead and just play it. Okay, so that was the audio file that we just downloaded. We're now going to import the audio file into Python. All right, and we'll have the wavefile.read. It returns two things, S and A. All right, so S is going to be the sampling, and then A is going to be the audio signal. All right, let's go ahead and print the sampling rate and then the audio shape that was returned. And so you can see it's 48 kilohertz or 48,000 samples per second. Now the shape is this long. That's you divide by 48,000 to get the number of seconds, and then you can see it's two channels. So that means it's going to be stereo, not a mono. Okay, let's display our original signal now. We have a number of samples. That's going to be NA, and that'll come from this number right here. And then the audio time duration is going to be NA divided by S. Now we want to plot the signal versus time. So if I go from, for the final duration, which is LA, the length of the audio, with NA time steps, and I create a subplot, and I look at the first channel, that's going to be my left, and then my second channel, that's going to be my right, and then I look at my time in seconds. So if I look at this, you can see, the very little audio here, a little click or beep right here, and then you can see the drone flight right here with a lot of magnitude of those two audio signals. You can see they're both different. So a little bit stronger on the left right here, and then it moved over to the right. So you could see just the magnitude of those two. All right, we want to convert to one channel. Just for this exercise, you don't necessarily have to do this, but I'm going to convert the audio segment from wave file. I'm going to get the sound, and then I'm going to set channels equal to 1. So I'm going to convert from 2 to 1, and then I'm going to have the modified version be put out here, and you can see that is going to create a new file I'll just move this over a little bit just so we can see these as we go. Here's the mono file. So there's the original one, the mono file that we just created. Now let's go ahead and import that new audio file. It's going to be this one right here, the modified one. And there's our sampling rate and our shape. So this one, you can see there's a missing number there in the tuple, so we're just going to have 1. So it's just a length of 387,072. And again, we still have the 48,000 hertz or 48 kilohertz, which is typical for audio. Now let's go and display the modified audio, and we're going to have the shape, and here's our time with the lens space, and I'll just make this purple because it's a combination of the blue and the red, and then we'll show the final signal. All right, so here's a combined one that combined those two channels into one with Pi Audio. So let's look at some frequency analysis now. When we want to look at audio signals, a lot of times we can look at the frequency and the different signals that happen in the different frequency ranges. So I'm going to analyze the entire audio clip. I'll do a Numpy fast Fourier transform on that. And you have to just take the final first half of it to get the information that you need. The second half you don't need for this analysis. And we want a single-sided spectrum only. Okay, so, all right, and then we're going to remove the imaginary part as well, if there is one, just get the power there, and then we have the frequency vector. So here I'm going to just arrange values so I can get the frequencies at which those signals occurred. And then we're going to plot the final value here. So here's our audio signal in the frequency domain. I'm going to plot from 20 up to 20,000. All right, and then here's the audible limit for humans. And then I'm going to set the X scale as log and the Y scale as log as well, just to be able to see it a little bit more. There's our amplitude and our frequency, and I'll show it. All right, so here's what humans can detect. And you can see a peak right here, and then another peak right out here. So this is going to be the drone out here. We're going to try to detect that. All right, human ears can still hear it, but if you had a microphone that could sample, up to 192 kilohertz or something like that, you'd be able to detect some of these ultrasonic frequencies that humans would not be able to hear, but other animals might be able to hear those, such as a dog. All right, let's look at the first second of the clip. I'm going to just do, this is when the drone is not operating. So I'm just going to plot that just like we did with the Fourier transform of the whole audio signal. And you can see you have amplitude versus frequency. Okay, and if I compare that to what I had before, you can see a lot of these higher frequencies when the drone is in operation. All right, but here you can see that it tails off. Most of the dominant frequencies are here in the lower frequency range. Again, not a lot of power, a lot of audio signal even. It's pretty quiet during that first second. All right, let's look at a spectrogram. This is a good way to look at audio signals over time. It combines the fast Fourier transform and this frequency analysis, but looks at kind of like a time plot, so you can see the audio signal over time. I'm going to create this from the signal.spectrogram, and we'll have our audio and the sample rate right there, and it's going to return these three things. Okay, the frequency, time, and the spectrogram. And I'll give it a log on the spectrogram just to be able to see it a little bit better in terms of, you're going to have, some frequencies that have a very high level and others that have very low. And so this log transformation helps to normalize some of those. All right, so here's our spectrogram for this. And you can see the amount of time that transpires, and then up to about 2.8 seconds, you can see that's where the drone turns on. And you can see this dominant frequency right here at about 16 kilohertz. And you can see some of these other bands right here. Those might be some of the other acoustics that are happening with this device or the room that it's in. All right, let's look at some features for machine learning. We might want to analyze an audio signal, and this is great for a human to be able to pick out certain features from the audio signal, but maybe we want to have a machine learned algorithm be able to detect certain things from the audio signal. All right, so let's go and bin the frequencies. This is going to be a way that we can assign a certain value for each range of frequencies, and I'm going to just create some bins. All right, in these ranges right here, these are my frequency bins, and then I'm going to have the audio signal level for each of these ranges. All right, and then I'm going to create a couple counters here, and then I'm going to go for I in range, the length of F. Okay, I'm going to put these into one of the bins. And so if I'm greater than this next level, okay, maybe I get to 10, I get above that, then I'm going to increase the value of was counted in that bin. And then if I look at the number of NB, I'm going to increment that by 1 as well. And I'm going to get the power for that. I'm just going to add that up. Okay, so I'm going to look at basically the audio signal level at each of those frequencies along the way and then sum them up. All right, then I'm going to look at for I in range length of FB, and I will normalize it by the number of samples that I counted for that level, and then I'll go ahead and plot it. All right, so it gives us kind of the mean sample level for each of these audio bins. And so you can see this is reducing it down quite a bit. So I do not have, maybe 20,000 values that I have to look at here, but I have, just a reduced subset where I've binned these into these different regions, almost like a histogram. All right, we can also look at the peak frequency as well. Let's analyze each second of the audio clip, and I'm going to take the number of seconds, I'll round down on this, and then convert it to an integer. And let's get our power, this of each frequency range. I'm going to get the maximum one from this range. And so I'm going to use this to try to detect the drone when it's on or when it's not. So let's go ahead and just use the 48 kilohertz here. Okay, and I'm going to do the FFT. I'm going to just do it by second here. Okay, so it's going to increment from 0 to 48,000 right here and just analyze just that segment. All right, and then once I do that, I'm going to get the power of the different frequencies, and then this one right here is going to say what is the maximum one. Okay, so the maximum power of all of those frequencies, and record that, and then I'm going to record that here with PF subscript I. So I'm going to look at the maximum of all of them and then record that, and then let's look at that graphically. Okay, so I'm going to plot the spectrogram right here, and then this shows me the peak frequency. Okay, so here it's down here at a very low value, and then the peak frequency here is up here around 16,000. So you could use this to detect a drone, where you say, well, I've detected something changed here, and the peak frequency is now up here at 16,000. Okay, so now I'm going to look at 2 additional audio samples to detect the presence of a drone. The first of the 2, which is the drone 2.wave, this is an easy one where the drone takes off and lands within the audio segment. And we're just going to modify what we've already done in this notebook to detect this drone. And then for the second activity, this is where a drone takes off far away and then moves closer. And, so we want to improve it beyond what we did with this simple analysis right here. and do something different where we might detect maybe how close the drone is and how close it's coming. Okay, so first of all, let's just go ahead and review what we've already done and see if you could take what was in the notebook and just modify it. Really, the only thing you need to do here is just change drone 1 to drone 2. Okay, but then just keep the parts that are absolutely needed for this analysis. So we're going to download it, and here's the URL. We'll go ahead and get the audio segment from Wave. We'll set the channels to 1. And so that is going to just reduce it down from stereo down to mono. And then we'll save the file, and we'll export it as a WAV file, and then we'll read it back in. There's our sample rate and audio shape. And then we're also going to get, analyze this new one, give us our time with lens space, and then analyze each second of the audio clip. There's the number of seconds that it goes on. And here we have our peak frequency, and we'll just record that for each one. Now we're going to analyze each segment and do our fast Fourier transform just on each second. Now, this is basically the same thing that we've done before, getting our frequencies and the power of at each of those frequencies. This is our argmax, tells us what's our peak frequency, and then we'll record that. And then let's go ahead and just plot this after we calculate a spectrogram. We'll show the spectrogram in the top, and then in the bottom we're going to show our peak frequencies. All right, and this is going to be drone 2. So let's go ahead and just run this. And here you can see it did a fairly good job of detecting the drone with this simple analysis. There's our peak frequency. Okay, and you can see the time where it takes off and lands. Now, let's go ahead and just copy this. Okay, and see how it does. Let me go ahead and copy it again. Copy and then paste it in here. Okay, and then let's just see how it does with drone 3 instead. All right, and you're going to see it doesn't do very well as it takes off and then lands a ways away. So it takes off. You can see, the audio signal is kind of weak here. It isn't quite at the peak level. And then when it gets close enough, then it starts detecting it. But even here, there's another one that's a peak frequency much lower. All right, and you can see some other noise going on here. There's some peak frequencies in this region. So it doesn't do a very good job of detecting the drone in this area. So let's go ahead and go ahead and do something else here. Okay, so we want to also import Numpy and Matplotlib. These are already imported, but just to make it self-contained. Okay, we're going to import drone 3. We'll go ahead and download the file like we already did, and then we'll convert that to mono, and then we'll read it back in as the mono audio signal. Okay, and then let's analyze each second of the audio clip. Now let's do something just a little bit different here than just looking at the peak frequency. So we're going to just say, okay, there's our peak frequency, PF, that we're going to record. But we're going to do something a little bit different. We're going to still take the fast Fourier transform every second of the audio data, but let's instead say PFI. We're going to sum up everything that's between the 15,000 to 16,000 range. Okay, let's just look at the power just right in this range, and maybe we can correlate that to distance that the drone is away from our audio microphone. Okay, so I'm going to look at PXX. I'm going to use np.where, and where the frequency is greater than 15 kilohertz and less than 16 kilohertz. I just want just that segment. I'm going to sum those up. All right, I want to normalize it maybe by my max over that whole range. So that the closest it can get is 1, and the furthest it could get away is 0. And then let's look at our spectrogram and then plot the figure. Okay, so now when we analyze this instead, we could see it didn't just do a 1 or a 0, but you could see it gave a range where it said this was the distance away that the drone is, and you could see as it got closer, it approached a value of 1, and the maximum was right in this region. All right, and then you can see it did a fairly good job here as well as the drone stopped. Then the signal tailed off again. So anyway, that's just a different way of doing it to be able to detect the drone. And there are many different ways you could do this. You could also take this spectrogram right here and use a convolutional neural network to detect the drone. So let me just show you a couple other possibilities. Here we have our audio, and I've discussed a few of those here as well at the very bottom. Much like we've done with something like concrete crack classification, you could also look at an image and then try to detect if there's a crack or no crack, or drone or no drone, just looking at the spectrogram. But in general, we're going to need many more spectrograms of this that are labeled with drone or no drone in order to do this convolutional neural network. So not possible just with these 3 audio segments that I've given you, but you could take a device that you have and be able to generate this data for training and for testing. So that would be one alternative way to do it, but there are many others that you could use as well. I hope this helps to just give you an idea of what we're doing with this audio detection and analysis. The most important things are going to be things like the frequency analysis that we showed, and then also things like spectrograms, be able to visualize those and analyze your audio data. But then you can also create features for machine learning like binning and other things. Okay, well, that's it for this one. The next one that we're going to go through is going to be up here, listed up here after audio. We're going to start doing some video now for the next one, where we import and analyze video using OpenCV.